guys, today we're going to continue the discussion that we started in class about moment of inertia. And today we're going to talk about how to find the moment of inertia using integrals. And then I'm going to go on and kind of show you how all of this ties together with torque and our angular kinematics, and we're going to do a couple of example problems. I'm going to keep the integrals pretty simple this time around, and if we have time, I'm thinking before the final, I can go into some more complicated ones, but for in the interest of time, we will wait on that. So this first slide just talks about the fact that the ease at which you can make something rotate is going to be dependent on a couple of things. It's going to be dependent on the shape of the object, the mass of the object, but it's also going to be dependent on what axis you're trying to rotate that object around. We have a couple of different axes we could rotate a baseball bat around. We could, if we wanted to, and if I can get to my white screen. It's not it. Okay. We could rotate it through the center like this, or we could rotate it around a center axis like this, or we could rotate it around one end of the baseball bat. I can make it go in a big circle around one end. So we have a couple of different options, and so when you look at your chart on page 264, you're going to see some different moments of inertia for the same shape, and that's going to, like I just mentioned, be dependent upon where is the axis of rotation. So let's take a look at the torque. We talked about how net torque is equal to the moment of inertia times the angular acceleration. But how would we find moment of inertia for something? Of course, they give them to you on page 264. But in case they're not, let's take a look at how to discover what it is for the moment of inertia for a configuration of particles. So things that don't make one total shape, individual objects, and then a continuous object, like a stick or a sphere. We're going to stick with the, we're going to do a hoop and a stick, I think, today in our PowerPoint. All right, this was something that we didn't really touch on that much in class, but the moment of inertia depends on the mass of the object, and it also depends on the distance from the axis of rotation that object is. So for a system of particles, you're looking at a sum. You're looking at the sum of the mass of the particle times r squared times the distance it is from the center of rotation squared. And if we're a continuous object like a sphere or a hoop or a stick or something like that, you would need to integrate along its shape or along its length. Sometimes that's very easy to do. Sometimes it's a little bit more complicated. But we're going to stick with more simpler ones today, I think. Okay. So let's look at a situation where we have particles, not a continuous object, and we're going to draw this on our whiteboard here. So let's say we have 4 objects, 4 spheres, and they are connected together by, we'll say these rods are massless for the purposes of our math. And let's say this distance here is 2b. And this distance here is 2a. And I want to rotate this whole thing around the center. I want to spin it on an axis here in the middle of the square. So I have 4 shapes. 1, 2, 3, 4. And those shapes have a particular mass. And all of those shapes are a distance from the center of rotation here. And since this whole length is 2a, that distance then will be a, is how far they are from the axis that I'm trying to rotate. So my moment of inertia for particles says that it's the sum of mr squared. So I have mass 1, and it's a distance a away, so that would be a squared plus mass 2, which is a squared plus mass 3, a squared plus mass 4a squared. Now, I'm not sure if it said that in the problem, but if all of these masses are equal and they are the same size particles, then you would just add these up, and your moment of inertia would be 4ma squared. It's pretty simple whenever you're dealing with particles. It's very similar to center of mass, kind of, but maybe even a little easier than that. So let's look at a situation where we have a shape. We already did all that. So we're going to look at a hoop first, because this is when you would need to integrate. So let's look at a hoop shape here. Oh, dang it. It's going to decide to wig out on me. Okay. Let's just pretend like that's a circle. And let's pretend like I'm going to rotate it through the center of that hoop. So I kind of drew my axis of rotation kind of coming out of the page like a z-axis. And I'm going to rotate it around that center point. So our moment of inertia is the integral of all the little tiny chunks of mass at whatever particular distance they are away from the axis. Now the cool thing about a hoop is that all of its mass is located on the outside of its shape. It has no mass in the center. So all of its mass is equidistant away from the center point. All of it's concentrated on the outside. So that means that my r squared value is a constant because the radius is the same for each part of this hoop. The mass is an equal distance apart. So that means that my my radius just comes out of my integral. And all I'm integrating is dm. And the integral of dm is just m, so the moment of inertia for my hoop is mr squared. And typically you'll see moments of inertia written in capital letters like that. So let's look at a situation that's not quite that easy, and let's look at a stick. Okay, so I have a stick, and I'm going to rotate it about its end down here. It's like we're rotating it around the y-axis, so it's going to flip around and come back and face us. And let's say that this whole stick has a length of L. And what we're going to do is we are going to find the moment of inertia by integrating along its length, right? So if we say that this is like the y-axis, then this rod is sitting along the x-axis. So as my x value changes, that of course is going to change the mass of the rod, and then that's also going to affect the moment of inertia. So what we're going to do is we're going to integrate from 0 to L x squared, which is the same thing as r, right, in this case. So we're looking at how the mass changes with the length as it goes down the length of the stick. And you guys should remember this from before, that dm is equal to lambda dx. We had that conversation before whenever we talked about the center of mass and integrating along the length of something to find the center of mass. So in this case, our lambda is mass per unit length, which is going to be the mass of the stick divided by its total length. So we can say dm is m over L dx. So now I can put this expression into this integral, and I can integrate the whole thing with respect to x instead of m. This just makes my life be a little bit easier when it comes time to do the integration, because the ml can just be pulled out of the integral, because that becomes a constant. And now all I'm integrating is x squared. So the integral of x squared is going to be x cubed over 3. And I'm going to look at this expression from 0 to L, or the whole entire length of my object. So that just means 0 is, of course, just makes the whole term be 0. And so I'm left with ml cubed over 3l. And then these guys cross out, and I've got 1/3 ml squared as my moment of inertia. Now, again, like I said, I'm not exactly sure if they're ever going to make you do that, but it's there for you and you've seen it once, and if we have time before the exam, we'll go back and review how to integrate along the length to find the moment of inertia. Okay. We can use something called the parallel axis theorem. Again, I'm just going to present this to you guys. I really doubt you'll ever have to use it, but it's a way to find the moment of inertia for objects if we know what the moment of inertia is for them, but we want to find a specific location away from the center of mass. So it's there if you need it. So for example, let me kind of show you guys what that means. So let's say I have a sphere, let's just say. Or let's just use a hoop thing since we already talked about that. And I know that the moment of inertia for an axis around its center is mr squared. But let's say I don't want to rotate it around its center. Let's say I want to rotate it at a point slightly off center from that axis. So I can use the parallel axis theorem, which says that the moment of inertia for the axis I know plus mh squared will give me the new moment of inertia for my new location. Again, don't think you will ever really have to use it, but I'm showing it to you just in case something does come up. It might be one of those things that you put in your calculator, and just in case, because I don't think it's in the formula chart. Okay, so how do I put all this together? All of this rotation business, all of this torque business, how do I put it together and actually solve problems? So this is kind of one that encompasses a lot of things, and then we're going to do one for a pulley, and then we'll be finished. So on this one it says the rear wheel of a bicycle turns as you pedal, the chain applying a force of 18 newtons at a distance of 7 centimeters from the rotation axis of the wheel. Consider the wheel to be a hoop of radius 35 centimeters and mass of 2.4 kilograms. What is the angular velocity of the wheel after 5 seconds? Okay, so we're going to have kind of a plan of attack for this. They want us to find the angular velocity. So it's obviously a kinematics issue. In order to do that, we need to find the angular acceleration. And in order to do the angular acceleration, we have to find the torque being applied and the moment of inertia of our wheel. So that's going to be our game plan here. So let's write down what we know. So we know that we've got this situation happening. We're going to need to use this equation. I can't draw that little angular acceleration symbol very well. All right, and we know that the initial angular velocity is 0 radians per second. So what we're left with is that the final angular velocity is going to equal our angular acceleration times time. And we already know our time to be 5 seconds. All right, so we need to find this guy. And we're going to use the idea of torque and moment of inertia to help us do that. So we know that torque is moment of inertia times angular acceleration. So angular acceleration is going to equal to our torque divided by the moment of inertia for our hoop. Now, they don't give us the torque in the problem. They gave us the force, and they gave us the distance that the force is being applied at. So torque is equal to Fd, or in this case it's F little r because they told us the radius of the wheel is 7 centimeters, or it's acting at a distance of 7 centimeters. Okay, and then we know that we've got a hoop, and I just showed you guys what the moment of inertia for that is. So that is mr squared. So what we have is angular acceleration is equal to torque divided by moment of inertia. If this was a translational or a linear problem, it would be acceleration equals force over mass, which is what you guys are used to seeing and doing. All right, so they told us that the force is 18 and that the distance is 0.07 meters, or 7 centimeters away from the center is where that force is being applied. The mass of our wheel is 2.4 kilograms, and the radius of it is 0.35 meters squared. So when we put this into our calculator, we can find our angular acceleration, and it's 4.29 radians per second squared. And then all we have to do is plug that into here with our 5 seconds, and we get a final angular velocity of 21.4 radians per second. So it's always helpful with these, just like in kinematics, to have a plan of attack. Go through and say, okay, I know I need this. How do I get that? Well, I need to find the second piece, and how do I get that second piece? Well, I have to do this third piece. So I had to do, I guess, 2 or 3 equations to get to